Consider a particle moving along a straight line. Initially, the position is x0, velocity is v0, and time is 0. The particle now starts moving with constant acceleration. The motion is repeated to emphasize the nature of accelerated motion. During the motion, acceleration remains constant. At the final position, the particle has position x, velocity v, at time t. The displacement is defined as x minus x0. These are the four equations of motion for constant acceleration. Today we will prove the equation v equals v0 plus at, under constant acceleration. We start from the definition of acceleration. Acceleration is equal to dv by dt. Now multiply both sides by dt. This gives a dt equals dv. Next, we integrate both sides of the equation. Applying limits of integration, time varies from 0 to t, and velocity varies from v0 to v. The right-hand side integrates to v minus v0. The left-hand side becomes a times integral dt. The integral of dt from 0 to t is t minus 0, which is simply t. So we obtain at equals v minus v0. Rearranging the equation, we finally get v equals v0 plus at. Hence proved. This is the first equation of motion under constant acceleration. We will now prove the second equation of motion. S equals x minus x0 equals v0 t plus 1/2 at squared. Velocity is defined as dx by dt. Substitute v equals v0 plus at into the equation. Now integrate both sides with proper limits. Split the integral into two separate parts. Integrate each term. v0 dt gives v0 t, and at dt gives 1/2 at squared. Applying limits, we get x minus x0 on the left, and t squared minus 0 on the right. Since t squared minus 0 is t squared, we simplify the equation. We know that displacement s is equal to x minus x0. Substituting displacement, we obtain the required expression. Thus, we obtain the second equation of motion under constant acceleration. Hence proved. We will now prove the third equation of motion under constant acceleration. Using the chain rule, acceleration can be written as dv by dt, which becomes dv by dx multiplied by dx by dt. Since dx by dt is velocity v, this simplifies to v dv by dx. Rearranging the terms, we obtain v dv equals a dx. Now integrate both sides. Velocity varies from v0 to v, and position varies from x0 to x. After integration, the left side becomes 1/2 of v squared minus v0 squared, and the right side becomes a multiplied by x minus x0. We know that displacement s is equal to x minus x0. Multiplying both sides by 2 and rearranging, we obtain v squared equals v0 squared plus 2as. Replacing s with x minus x0, we obtain the final form of the equation. Hence proved. Now we prove the fourth equation of motion under constant acceleration. We start from the first equation of motion, v equals v0 plus at. Rearranging this equation, we obtain at equals v minus v0. Now we substitute the displacement equation. We rewrite at squared as at multiplied by t. Substituting the value of at from the first equation. Expanding the expression. Separating the terms. Taking a common denominator of 2. Combining like terms. Thus, s equals v0 plus v divided by 2, multiplied by time. Since displacement s is equal to x minus x0. Hence, the fourth equation of motion under constant acceleration is proved.